Over here you will find a lady trying to balance a paper butterfly at the tip of a finger. Now no matter how much or how hard she is trying, she is unable to do so. Now notice what happens when she balances it at one particular point. As you can see in this case, that she is able to balance the butterfly. Now the case is that not at any point or every point will the butterfly be able to balance itself on the tip of the finger. But there will be one particular point which is unique, at which the lady will be able to balance the butterfly on her finger, as you can clearly see. So let us find out what exactly is going on. We consider a similar paper butterfly like the one the lady was balancing in the video. Now this entire paper butterfly is an object and it is made up of many atoms. Now this butterfly, this paper butterfly, has a certain weight with which the earth exerts a pull on it towards its center. Now this butterfly, being made up of many atoms, each atom will also have a certain weight acting in the downward direction. So when we consider this paper butterfly as a whole, it is not only that this entire object as a whole has a weight, every atom also has a weight, and this weight is due to the Earth's gravitational pull. Thus we can say that the Earth attracts every atom towards its center by a force which is known as the force of gravity. This force of gravity acts on every atom present on this particular object, and it is also known as and can be considered as the weight of the given atom. So when I consider one single atom, it also has a certain weight, no matter at which point of the butterfly I consider it. So every atom that this paper butterfly is made of has a certain weight W. So now let us try to find out how the lady was able to balance the butterfly on the tip of a finger. Let's say we consider a point and call it A on the object. Now if I draw an axis at A, I will find that there are more number of atoms on the left hand side of the axis than on the right hand side. So if I consider the atoms all around, I can clearly see that the force acting on the individual atoms on the right hand side is much less as compared to the force acting on all the atoms on the left hand side. Why? Because the number of atoms on the right hand side are much more. So this means that the clockwise moment will be much more than the anti-clockwise moment, and we can say that about this point A, we will not be able to balance the paper butterfly. Why? Because the algebraic sum of moments due to weight W of each atom about point A is not 0. This is because the clockwise moment is greater than the anti-clockwise moment. Similarly, if I consider another point, let's say somewhere here, and I call it B. Again, if I draw an axis through B, I will find that there are more number of atoms on the right hand side of the butterfly than the left hand side. So if I consider the atoms on the right hand side of the butterfly and consider the weight on each atom, then because there are more number of atoms on the right hand side, the total force will be more, due to which the clockwise couple will be more. Now if I consider the left hand side, because there are a less number of atoms, the total force will be less, which means that the anti-clockwise moment will be less. This leads us to the fact that the anti-clockwise moment is greater than the clockwise moment. The algebraic sum of moments due to weight W of each atom about point B is not 0, and because the algebraic sum of moments is not 0, the butterfly cannot be balanced at point B. So now let us consider another point G, that is somewhere over here. and again I consider an axis through point G. Now if you notice closely, doesn't it seem like the number of atoms on the right hand side are equal to the number of atoms on the left hand side? So what will this mean? This will mean that the force exerted, that is the total force exerted on the right hand side, will be equal to the total force exerted on the left hand side, or in other words, the clockwise moment will be equal to the anti-clockwise moment. So we find that at point G we will be able to balance the paper butterfly, and this is true not only for the left hand side or the right hand side, this is also true if we consider the top or the bottom of the paper butterfly. Even at those points, if I consider an axis like this, all the points to the top will have a force in the downward direction that will be equal to the force on the other direction, or in other words, the clockwise couple about this point will be equal to the anti-clockwise couple about this point, even if I consider the axis perpendicular to this axis. This means that the algebraic sum of moments due to weight W of each atom about point G is 0. Now since the algebraic sum of moments about point G is 0, what can we say? It is only because the sum of torque in the anti-clockwise direction or the anti-clockwise moment is equal to the sum of torque in the clockwise direction, that is the clockwise moment. So at point G, because the algebraic sum of moments is 0, we are able to balance the paper butterfly. Thus we see that it is at this point G which we can balance the paper butterfly. This point G is known as the center of gravity of the given body, and it is at the center of gravity where we can consider the entire weight of the body is acting, and it is due to this reason that this point is known as the center of gravity. So what are the basic characteristics of the center of gravity? We found that center of gravity is the point through which the entire weight of the body is considered to be acting. Furthermore, we can say that the algebraic sum of moments of the weights of the atoms constituting the body is 0 about this point, or in other words, the clockwise moment is equal to the anti-clockwise moment, and this is why the body will be in equilibrium position about this particular point. Furthermore, we can say that any body can be balanced by supporting it at its center of gravity. So in the previous case we saw that when the lady held up the paper butterfly on the tip of her finger at point G, she was able to balance it. So let us find out the various centers of gravity of different objects. Now these are regular objects, like you can see a rod. Now this cylindrical rod will have a center of gravity at its midpoint. So this point, which is the midpoint of the rod, will be its center of gravity or its CG. Similarly, if we consider certain 2D objects like a parallelogram or a rectangle or a square, their centers of gravity will be at the intersection point of diagonals. So in all these cases you will find that at the point where both the diagonals intersect, that point is the center of gravity, and these objects can be balanced at that particular point. Similarly, if we consider a circular disc, then the center of gravity of the circular disc will lie at its center. So the center of the disc is the center of gravity of this circular disc. Similarly, if I consider a triangle, that is another 2D shape, the center of gravity will also lie at a point that is the intersection point of the medians. Now what is a median of a triangle? The median of a triangle is that line which we draw from a vertex which bisects the opposite side. So the intersection point of medians will give me the center of gravity for the triangle. So I have been talking a lot about the center of gravity of certain objects that have a regular shape. Now, how do we find out the center of gravity of an irregular object? In this video, I will demonstrate to you how the center of gravity of an irregular object like this paper cutting, as you can see, can be found out. So firstly, we consider a supposed center of gravity, that is that point marked. Now we hold up the paper cutting, as you can see, by a very sharp pen or pencil. Now from the nib of the pen or pencil, we hang a very light weight with means of a thread. Now you will find that at one particular position, the thread becomes stationary. So we take that particular line given by the thread and mark it out with the help of a pencil. As you can see, is being done in this video. So this line being marked out by the pencil will give us a reference line. Now we repeat this procedure for two other points in the same irregular body. We consider another point at the top of the body. We pierce it with the sharp pen or pencil and we hang the light weight with the help of the thread. Again, it becomes stationary at a point. So marking out the thread with the pencil, we draw a line. Now this gives us the second reference line. We again repeat this procedure for a third point at the other end of the irregular object. As you can see, we repeat the procedure, and where the light weight becomes stationary or stable, we mark out that line given by the thread with the help of a pencil. So as you can see, this line has been marked out by the thread and we mark it out with the help of a pencil for reference. So this is the third reference line. Now you will notice that all these three lines will be intersecting at a point. Now we will intersect these points with one another at either end of the given irregular object. So we consider the middle 2 points first and we mark it out with a pencil. Similarly, we consider the points on either end of the object. We mark that out with a pencil as well. So on marking these points, we are getting the reference lines that had been marked out by the thread. Now you will notice that all these 3 points are intersecting at a certain point. These 3 lines that have been marked out are intersecting at a particular point. This point is the center of gravity of the given object. Now you will find that if the object is balanced at the intersection point of these lines, it can be easily balanced. Notice how the obtained center of gravity is different from the supposed center of gravity. Now you will find that if the entire object is balanced at CG, it will be balanced. But if it is tried to be balanced at point P, it is not balanced. So here you will notice that the person is piercing this entire object at its CG, and the moment it is balanced at CG, you will find that it does not fall off. But what do you think will happen if it is tried to be balanced at P? There it falls off because P is not the center of gravity. So this proves that at the center of gravity, which we found out in this case for an irregular object, any body can be balanced. In this video, you will find that a man is walking across the Niagara Falls, and this is where the practicality of center of gravity comes into play. It is practical even in these sports where with the help of this very long rod that the man is carrying, he is able to balance his center of gravity about the very thin rope that he is walking on. So center of gravity not only has mathematical applications, it also has practical applications in sports like the one you saw in this video.